Today I will present our work on building massive MIMO baseband processing in virtualized radio access networks with a new hardware setup called single-node supercomputer. So nowadays, the mobile traffic is increasing very rapidly. One could anticipate that there will be more mobile and IoT devices, and data traffic among them will also increase significantly. To meet the increasing mobile traffic, people are trying to deploy more radio units with higher number of antennas and support more users. Therefore, the massive MIMO are promising to serve the large mobile traffic. On the other hand, the adoption of virtualized radio access networks, vRAN, is gaining more interest. vRAN replaces proprietary and specialized hardware, such as DSPs and ASICs, with commercial off-the-shelf servers in baseband units. This transition brings several advantages, including vendor lock-in mitigation, flexible deployment, better operational feasibility, and reduced total cost of ownership. However, this convenience comes at the cost of imposing greater computational demands on the commercial hardware, which must now handle the intensive processing requirements of modern cellular networks. So here is a typical baseband processing pipeline. The basic unit is a FLAPE, which consists of multiple symbols. Each symbol processing will go through a bunch of tasks. For example, in the uplink symbol processing, we have 4 tasks typically: fast Fourier transform, equalization, demodulation, and DPC decoding. There is also a special pilot symbol, which only consists of 2 tasks, FFT and channel estimation, whose result will be used in both uplink and downlink processing. Each processing task is non-trivial and requires high-dimensional matrix multiplication and inversion. In addition to computational complexity, there are also string and latency requirements for each frame. For example, URLLC frames requires to be processed within 1 millisecond. Prior solutions can be categorized into 2 groups: general-purpose x86 servers and domain-specific accelerators. General-purpose x86 servers, such as Big Station and Hydra, uses distributed architecture. They are easy to program and deploy since hardwares are widely available in the market, but they suffer high management cost and large physical space. On the other hand, domain-specific accelerators such as Lumami build a testbed with 50 FPGAs. It is more energy and cost efficient with smaller physical space, but they suffer from management inflexibility and limited reconfigurability. When the traffic is diverse from configuration, it will lead to low hardware utilization. Therefore, existing hardware is inadequate to provide scalable computational power, high programmability, and flexible deployment. So let me introduce the new hardware we used in this paper. The single-node supercomputer consists of a single host server with a composable GPU pool, and they are connected with a load-store interconnect, such as routable PCIe. A switch enables multiple accelerator traces to be connected to the single host. This architecture can be fit into a single rack, so it is physically compact and reduce the management overhead. SNC can also provide the following benefits. First, the host native system stack allows us to apply CUDA programming model and use existing SDKs so that the remote GPUs can operate as the local ones. Second, it allows us to add or remove GPUs on demand without host interruption. Third, in the SNC, GPU and GPU communicate through the external fabrics, bypassing the host. This allows us to achieve consistent inter-GPU communication bandwidth. All these benefits make SNC a good candidate for massive MIMO baseband processing. Given these benefits, the question is how can we effectively unleash the power of SNC to process massive MIMO baseband processing? We found this is non-trivial due to the mismatch between the software and hardware parallelism. So the software parallelism or massive MIMO can be categorized into 3 levels: frame, symbol, and text level. Frame level parallelism is the most coarse-grained one. It parallelizes the processing of different frames. Symbol level parallels symbols within a frame, but it needs to deal with the dependency between the pilot symbol and the uplink or downlink symbols. Text level is the finite grained one, but it also suffers from dealing with more complicated data dependency issues. The hardware parallelism can be categorized into 4 levels. Assume P is the required resource by a job, and Q is the available resource in the GPU pool. So the first one is full parallelism, which means that there are enough resources in a single GPU for a job to run. The second one is fragmented parallelism, which means that the total amount of resources are enough, but they are spread across multiple GPUs. Therefore, inter-GPU communication is necessary. The third one is partial parallelism, which means there are inadequate resources among all the GPUs in the pool. The last one is delayed parallelism, which means that currently there are no resources available for the job, but it will be available in the near future. When the system is running, one should fully exploit the 3-level software granularities to parallelize frames, symbols, and texts as much as possible. However, this makes hardware parallelism keeps evolving and becomes irregular. Therefore, the key challenge is how to build a gap between the software parallelism and hardware parallelism. The key idea of our system is to dynamically adjust software granularity based on the hardware parallelism. We design a system megastation which keeps track of the hardware status of each GPU and then choose the best GPU and the software granularity accordingly. Megastation inspired by dynamic instruction scheduling from computer architecture field. We model the SNC as a tightly coupled microprocessor and design 3 components: instruction unit, scoreboarding, and pipeline scheduler. The instruction unit passes and analyzes instructions. The scoreboarding tracks GPU status and instruction execution. And the pipeline scheduler schedules instructions to GPUs. So instruction unit first translates frames into symbols and further parse symbols into 11 types of text instructions according to the symbol path showed in the previous slides. Then it analyzes the data dependency between instructions during processing. For example, for the uplink job, the equalization instruction depends on the output of FFT and zero forcing instruction. The final structural analysis groups instructions with data locality and labels each group with candidate GPUs. The way we do structural analysis is based on a characteristic experiment in the paper, which calculates how diverse software parallelism are affected by irregular hardware parallelism. The scoreboarding maintains an instruction table to check the status of each instruction, which contains the instruction ID, the required resources of the instruction, and the execution time. It also maintains a GPU table to check the status of each GPU, which contains the GPU ID, include instructions, and a flag recording whether an instruction has completed. Inside each GPU, we maintain a flag map in each global memory. When an instruction starts and completes, it will set the corresponding flag in the flag map. A daemon in the host is busy pulling the flag map to check the status of each instruction and updates two tables accordingly. The overall discipline of pipeline scheduler is list slack time first. This helps us to guarantee that each instruction will be completed before its deadline to meet the latency requirement. After the most urgent instructions are scheduled, we use three strategies to maximize the GPU usage. First, we reorder the instructions so that the idle SMs can be filled with instructions that require less resources. Second, we coalesce instructions with data localities into one stream and avoid data synchronization overhead. Third, we also overcommit the GPU resources to avoid scheduling runtime between CPU and GPU. We conduct our experiments on a GigaIO FiberX platform, which NVIDIA A100 and V100 GPUs. We compare MegaStation with three baselines: Lumami, Hydra, and Big Station. Since previous works are on different platforms, we re-implement them on our platform following the same scheduling strategy. We evaluate end-to-end throughput and tail latency using 6 A100 GPUs on SNC. We use the same latency requirements as previous works, which is 4 milliseconds for a 1 millisecond frame. Overall, MegaStation can achieve up to 3 times throughput improvement in end-to-end evaluation without exceeding 4 millisecond deadline. And we can support up to 256 times 128 MIMO. For throughput evaluation, the x-axis is the MIMO configuration, and the y-axis is the reported throughput, whose unit is 1,000 frames per second. If you look at 256 times 128 downlink MIMO, MegaStation achieves about 27% higher throughput than Lumami GPU, and 61% higher than Hydra GPU, and 2.5 times higher than Big Station GPU. For tail latency evaluation, the x-axis is also the MIMO configuration, and the y-axis is the reported 99.99% tail latency, whose unit is billion second. If you look at 256 times 128 downlink MIMO, MegaStation achieves about 50% lower latency than Lumami GPU, 44% lower than Hydra GPU, and 56% lower than Big Station GPU. We also conduct several other experiments. For example, we evaluate the scalability by changing the number of RUs and GPUs, and also discuss the impact of heterogeneous GPUs. We also conduct a drill-down experiment to show how each component of MegaStation contributes to performance improvement. If you are interested, please refer to our paper for more details. To conclude, vRAN is being adopted and requires high computing power. The NSDI is an emerging scalable computing platform for the vRAN application. However, we need to match software and hardware parallelism to unleash the power of NSDI. Our main contribution is to close the gap between baseband processing and SNC via an application platform called design system. The key idea is to adjust software granularity based on the hardware status. MegaStation models are SNC as a tightly coupled microprocessor with 3 components: instruction unit, scoreboarding, and pipeline scheduler. Evaluation results show that MegaStation supports up to 256 times 128 MIMO, with 66.2% lower latency and 2 times higher throughput than previous work in end-to-end evaluation. The code is also available on GitHub at the link below. Thank you for your attention. I'm happy to take any questions.